Welcome back to another fun-filled physics video. I'd like to talk to you guys a little bit about energy of an oscillator. This is going to be, so in the case that there's no friction, right, there's no way to lose energy. So for a simple harmonic oscillator with, nothing else going on, so our energy should be constant because we're not losing it to air resistance, we're not losing it to friction of the string on the pendulum or friction of the block on the table or anything like that. Heating from stretching and contracting the spring. So we're saying all of those factors don't exist right now. We're doing the ideal case, once again, spherical chicken in a vacuum. So if I look at total energy, phonograph, total energy versus time. I mean, this is obviously, since it's constant, we know exactly what it's going to look like. It's going to be flat line, right? But I'm graphing this to prove a point in a minute. And you'll see in a little bit. So what if I wanted to graph kinetic energy? Well, for that, I might want velocity, right? So do I have a velocity equation? So our kinetic energy should be 1/2 mass times velocity squared. And our velocity equation, let's use what we used earlier when we wrote out those equations. Let me check my notes. We said V0 cosine omega t. Is what we'll use. All right. So that means my kinetic energy should be 1/2 the mass times V0 squared times cosine squared omega t. So that's going to look like a cosine squared graph. So this should be start positive, right? Because if cosine of 1 is 1, so it should go to 0. That was a text message. And go here, and should oscillate like such. And once again, drawn poorly, but so is everything else. It's fine. So this should look like cosine squared. Ooh. Whatever. That's going to be a cosine squared graph. So what should my potential energy look like? Because that's the other factor, my total energy. Well, I'm glad you asked, student. Oh, you can't see the bottom of that. Oops. I'm glad you asked, student. Because we know that the total energy is constant, right? Now I could probably figure this out by doing something where I say, something where I could do for a spring, I could do potential energy is 1/2 kx squared, right? And we said x was equal to x naught times sine omega t. And so that tells me that our potential energy should be 1/2 k x naught squared sine squared of omega t. Right? So this graph should look not terribly unlike the other. I'm going to try and make it, you can't quite see it all. So if I bring down my points like I did before, like that, and say this is going to be potential energy, or U if you'd rather. No pun intended. this one will look something like this. Right? And this is going to look like a sine squared graph. So, but earlier I said that it should add to 1, right? It should add to a constant, because that's what we're looking at up here. Well, this is going to actually help me relate things, because I know that my total energy is equal to my kinetic energy plus my potential energy. I'm going to use U. So, and I'm going to use this is my base for my kinetic energy. So if I say when my potential energy is maximum, my kinetic energy is 0, right? So those are in the same line. Then I know that my total energy would be equal to 1/2 kx squared, or x naught squared, right? 0 plus 1/2 k x naught squared. But, I mean, I can also do it the other way. I could say that 1/2 mv naught squared is equal to your total energy for if I choose the other point where this is 0, where this is 0, and this is not. So now I know those are going to equal each other. So maybe I can figure out how to relate this x naught and this v, right? So what I can do is I can say that 1/2 k x naught squared is equal to 1/2 m v naught squared. Cancel these halves because no one cares. And let's solve for v naught and just use x naught as our basis. So v naught is going to equal to square root of k over m x naught. That's a k. I don't know how well you guys can tell that. Maybe I'll just write it again in case you can't. And x naught's our amplitude. So let's do the last magic step here. I might actually need more paper for this. So I started without you a little bit. We've got, these are what we know. So these are my equation for x, my equation for v, and I know this relation now. So I can rewrite my equation for v, and I can say this is going to be square root k over m x naught cosine omega t. Well, do you remember before when we looked at an equation and I said to you that we could say that v is equal to a, our amplitude, or x naught in this case, times omega cosine omega t. So I've learned a couple things here. Well, in another video we're going to talk about how omega is the square root of k over m, but I've also just pulled it out here too. So I can say v equals square root k over m, or I just wrote it again. I say v equals x naught omega cosine omega t. And so, and then now when I go to my, this is the point I was going to make. I kind of got sidetracked. So when I look at my energy equations, though, let me write those out for you. I'll pause it real quick. I can get to here, but I have to actually square this term, right? Because that's squared. So then let's just rewrite this again and pull it out at 1/2 k x naught squared. Oop, I forgot to square the sign. Sine squared omega t plus 1/2 m times k over m x naught squared cosine squared omega t. So this m and that m cancel. Oh, forgot to square my x naught here. It's real important to track your algebra very well. You know, those transcription errors going from one line to the next is one of the most common errors, at least for me. I mess that up all the time. And now all of a sudden our numerator is the same. So now I can factor that out. I can factor out 1/2 k x naught squared, right? And I can say that I have sine squared omega t plus cosine squared omega t is my total energy. Ready for the magic step? Because I said total energy is constant. This still depends on t, right? But we know that sine squared x plus cosine squared x or y or t or theta, whatever you want, is equal to 1. So now I've just proven my total energy is a constant, like we predicted at the beginning. Alright, I'm going to call this an end to this video. I'll see you in the next one, guys.